In Lab 1, we are observing the motion of an object moving at constant velocity and constructing a computational model of the object's motion. Studying experimental data in comparison to predicted data will be important in understanding the motion of objects under optimal conditions in comparison to real conditions. An object moving at constant velocity indicates that the object is moving at a constant speed in the same direction. Newton's second law, which states that the acceleration of an object is dependent on the net force acting on the object and the object's mass, can be applied to explain an object's motion. Additionally, the ratio of the change in velocity to the change in time is equal to the total pushes and pulls, or the net force on the object divided by mass. Therefore, for an object to have constant velocity, the net force on the object must equal 0. In this lab, I chose to analyze a video of a basketball rolling on a flat surface. I will be analyzing the video from frames 88 to 120 because the ball is still speeding up from rest in the beginning of the video and will be slowing down near the end of the video. The calibration stick is set to the diameter of the ball, which is 0.239 meters. The origin axis is set to the center of the ball with the positive x-axis to the right. Since the ball is traveling to the left, it is moving in a negative x direction. The position versus time graph of this motion is displayed on the right. In Tracker, I also could have picked alternate orientations for the axis. For example, if I chose the left of the origin to be the positive y-axis, the ball would be traveling at the same speed. However, the ball's velocity is now in the positive direction and in the y component. Thus, the ball's position vector would only be changing in the positive y direction. The position versus time graph with the new orientation would display a positive slope. From Tracker, I obtained the observation start time, the time of the last observation, and the ball's initial position vector. I calculated the ball's initial velocity vector using the first two position data points and the corresponding time data points. Using the data from the experiment, I created a computational model of the ball's motion in GlowScript. In line 31, I input the ball's mass, which is 0.62 kilograms. Line 34 indicates the ball's initial position vector, which is 0, 0, 0 meters. Line 35 indicates the ball's initial velocity vector that we calculated earlier, which is negative 1.30300 meters per second. Line 38 indicates the beginning of our observation time. In line 39, I changed the model's time increment to be the same as the observational time step from Tracker, which is 0.033 seconds. Line 48 indicates that we want to create a model from 0 seconds to the last observation time at 1.068 seconds. Since we want to create a model in which the ball has constant velocity, the net force vector is set to 0, 0, 0 newtons in line 53. Line 57 has been modified to display Newton's second law. Note that since the net force vector is set to 0, 0, 0 newtons, the mass of the ball is negligible. Additionally, the final velocity is equal to the initial velocity, so the velocity is constant. Lastly, line 59 has been modified to display the position update formula. The code generates this model and graph of the ball traveling at constant velocity. This graph compares the ball's experimental position to the computational model's predicted position. Velocity is the rate of change of position with respect to time. Therefore, the slope of the position versus time graph is the velocity of the object. In the graph, the purple line represents the predicted position of the ball from the computational model. The linear slope indicates that the ball's velocity is constant and therefore the net forces acting on the ball are equal to 0. In comparison, the red data points represent the experimental positions of the ball taken from Tracker. Since the data points are not perfectly linear, it can be concluded that the velocity is not constant during observation. The discrepancy between the model and the experiment can be attributed to the non-zero net forces acting on the ball during observations. This diagram illustrates the forces acting on the ball during the time of observation in the experiment. In the y component, the force of gravity is acting on the ball in the negative y direction, and the force of the pavement acting on the ball is in the positive y direction. Since these forces are equal to each other in magnitude but opposite in direction, the net force is equal to 0 in the y direction. Since there is no initial velocity or acceleration in the y direction, the position of the ball in the y direction never changes. In the x component, there was an initial push to set the ball in motion, but that force has been accounted for with the ball's initial velocity during the time of observation. In the positive x direction, the force of friction is acting on the ball, causing the ball to slow down. Other forces such as wind resistance could have also impacted the ball's motion. More accurate tools are required to determine all forces acting on the ball. To improve prediction and observation agreement in the future, the experiment could be conducted on a surface with less friction to decrease the net forces acting on the object. In conclusion, an object with constant velocity experiences no acceleration since net forces acting on the object are equal to 0. The computational model illustrates the ball's motion under ideal conditions of no net forces. The experimental data's deviation from the computational model indicates that there are non-zero net forces acting on the ball, such as friction.